We are going live on YouTube now. Okay, just so you know it. Well, let's start. Then, well, people are still joining us, but let's start. I will do a short introduction and then I will pass you the floor, okay? Thanks. Hello, everyone, and welcome to another talk in our webinar series. Today we have Santiago Ávila from the Universidad Autónoma de Madrid talking about the effect of galaxy halo on galaxy clustering, on galaxy halo connection on galaxy clustering in the advent of stage 4 experiments. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel. Just search for LIneA MCTI. Santiago, thank you very much for being with us today, and the floor is yours.
Okay, thank you very much, Rodrigo, and everyone in LIneA for organizing this. So yeah, I'm going to talk about some kind of recent work we did in EVOS, analyzing what is the effect on the connection between galaxies and halos, and what is the effect on galaxy clustering. And I will put this in the context on how we are basically changing from the stage 3 to the stage 4 experiments on the dark energy. Well, I'm a postdoc with the Marie Curie program in the Institute of Theoretical Physics in Madrid and the Universidad Autónoma. Okay, so I have divided the talk in several parts. One, I start by a broad motivation of why we want to study galaxy clustering and why it's useful for cosmology. And then I will introduce the different input to the project. So what is EVOS, the mission line galaxies that we used, the body simulations called AutoRim that we are using, the modeling in which we based all our analysis, which is the halo copulation distribution model. And then we start dissecting this model and then changing the assumptions that go into it to see how it could affect the clustering of emission line galaxies. And later we take that model and feed the free parameters to the data from EVOS. And we also discuss what impact this could have on cosmology. And then that leads us to look at future surveys in the outlook and conclude. Okay, so I guess you have all seen this picture before. To say we live in an accelerated universe and we want to understand dark energy better. We have a lambda CDM model, which is the concordance model of cosmology. And in that context, I want to say what is the contribution from the large scale structure. One of the main contributions from large scale structure is the constraints from BAO, baryonic acoustic oscillations. These are some waves that happen in the early universe when the universe is made of a hot baryonic photon plasma. And this plasma is held for the beginning of the universe until the moment where the temperature drops below 3000 Kelvin. Here we have a hot plasma in which baryons and photons are coupled, and after that, this plasma is not coupled anymore, so the universe becomes transparent, matter becomes neutral, and the light can travel free. So, because we have some initial perturbations due to inflation, and because we have this pressure within the plasma, this interaction between photons and baryons, sound waves can propagate. These are basically pressure waves. And these waves keep propagating all during this epoch until the moment where the temperature drops and the universe becomes transparent. And that moment, that waves don't propagate anymore, and they leave imprinted the shape of the waves, leaving like a preferred scaled distribution of matter in the universe that we can exaggerate here in this kind of frozen waves here. What happens after decoupling is that these waves are still frozen there, but the universe keeps expanding. So we can basically use this preferred scale as a standard ruler. We can find this both in the CMB, in the two-point correlation function of the CMB, but also on the distribution of galaxies or other traces of matter in the large scale structure of the universe. I will focus on this talk basically on the latter, on the galaxies. So for galaxies, the BAO is seen as an excess of pairs separated by about 100 megaparsec over H in co-moving distances. This is the BAO feature as measured by the Bose collaboration with the large luminous red galaxies in redshift 0.2 to 0.5, and this is a very clear feature measured with a 1% accuracy. And basically this is by measuring distances between galaxies, finding pairs of galaxies, and we find an excess of pairs around the BAO scale. As I was saying, this scale, we want to detect it because we want to use it as a standard ruler. If we know the size of it, we can do the standard ruler technique in the same way we use supernova to use the standard candle technique. And this gives us some sort of Hubble diagram in which we can represent distances versus redshift and see the expansion history of the universe. Here is a representation with different BAOs, even if those BAOs are a bit old now, but we can see a few BAOs and basically a lot of supernovae, and all of these constraints the expansion history of the universe. This gives us constraints via the angular diametric distance that depends on the cosmological parameters such as omega k, omega mater, omega lambda, etc. And also we can measure not only the angular size of it, but we could also have a ruler on the radial direction, and this gives us a constraint directly on the Hubble rate, on the expansion rate of the universe. That also constrains the cosmological parameters. This is another representation to see how we can measure the expansion history of the universe. In this case, expansion rate history. And we can see the moment where the acceleration starts in the universe. So that's why BAO is very interesting to study dark energy, because we can see this moment of acceleration. And these are the 6 measurements done by the SDSS collaboration that includes Bose and eBose. So BAO has contributed, it's basically a pillar of the lambda CDM model. Even if dark energy was first discovered by supernova studies, I think when it came very, very clear that it was there, it was when we combined supernovae with BAO and CMB, and we saw that the 3 of them were hitting the same place in this plane of omega lambda, omega mater. It's a bit of a historical plot, let's say, and in the 2010s approximately. But 10 years later, we have this one released last summer by eBose, in which basically we have reduced a lot there, but we still have supernova BAO. We see that BAO is now much narrower, and also we have CMB here, also much narrower. So this is by combining all this expansion history that I was showing in the previous slides. I also wanted to mention, I have put here the 6 measurements by SDSS, but there are other collaborations that have measured BAO, such as WGLC, 6DSF, but I wanted to bring also the attention to the Dark Energy Survey, in which I also collaborated, and some people in the audience as well from Brazil. So we measured this BAO with GR1 with a 4% accuracy, and we expect to measure it around 2%. And in this case, we are only measuring the angular distance, so it's quite accurate for an only angular distance. We see a clear signal there. This is only GR1, and we expect to have much better constraints in GR6 that should be coming up, GR3 coming up very, very soon. And this is all the references that led to these measurements in the GR1 analysis, but we hope to have soon also the GR3 papers. And okay, let me just come back a bit to the clustering, to the 2-point correlation function. Basically, I was mentioning the counting of pairs. I will talk a lot in this talk about the 2-point correlation function. which can be defined as the excess probability of finding two galaxies separated by a distance r with respect to a random distribution. So we count galaxies separated by distances in certain bins, and we see what is the excess of pairs with respect to a completely random or uniform distribution. Is here where we can see a clear BAO signal around 100 megaparsec, but we can study something more than that. We can, because the physics on the angular and radial directions are not the same. If we have the observer here, there are certain effects, such as the redshift space distortion that I will talk about later, that will only occur on the radial direction. Sometimes we want to separate between the angular scales and the ones which are along the line of sight. So we will measure either this isotropic one in R perpendicular R parallel, or also distance plus orientation, which orientation is the cosine of this angle. And then we can do multiple expansion around this angle. So we can do the monopole, which is basically isotropic function again, or the quadrupole, which is very sensitive to the line of sight. So we will study this when we want to study more the velocities. Also, we have the projective correlation function that it's only sensitive basically to the angular scales. So we'll use this one to basically analyze mostly on logarithmic bins, the H2D model, and in particular what happens in real space, rather than because we are not using any of the pairs along the line of sight. So we care only about real space with respect to redshift space. Okay, so what is redshift space distortions? Basically, we have matter in the universe, and we know that these overdensities will also create a divergence on the velocity field. It will attract matter from both sides. That's what creates this divergence. And then the velocity field then becomes correlated to the matter field itself. So when we do two-point correlation functions, we have this kind of boost factor predicted by Kaiser. And in this boost factor, we have this F factor, which is the growth rate of a structure. So tell us how fast matter is being attracted to other matter, to other densities, okay? So it tells us what is the strength of gravity, how fast things are falling due to gravity. And this gives us constraints on cosmological states of gravity. So basically it's a test of general relativity. That's why by exploring redshift space distortions, we can not only explore the background cosmology, but also the perturbation cosmology, and see if there is any modification of gravity there. So far, results say everything is compatible with GR, but any deviation from zero would imply deviations from GR. So the aim of SDSS and its program, the extended baryonic acoustic oscillation spectroscopic survey, is basically to do these three-dimensional maps of the universe by studying spectra of different galaxies, to do these accurate maps to measure both BAO and redshift space distortion. And it concluded last summer, releasing all these measurements and all these cosmological constraints on omega K, omega matter, the question of a state of dark energy, H0, etc. And one of these samples is the mission line galaxy samples, which I will focus on later. So this release I was talking about was made of around 20 papers that summer, but there is also more historical papers on BOSS or even the original SDSS main galaxy sample that has contributed over 20 years to finally get all these constraints. And you can Google for the eBOSS results and you will find this nice website. But mostly the work I want to talk about is the one that I led with tight collaboration also with Violeta and the rest of people from eBOSS, in which we study the mission line galaxies halo occupation distribution model. So then this is the end of the introduction, and now we go to see what are the ingredients that we need to build our model. So we need an embodied simulation, we need the eBOSS from data, the ELGs, with redshifts and angles positions in the sky, and then our halo occupation distribution model. So the footprint of the mesoline galaxies is this one. We have one south galactic pole around the equatorial plane and the north galactic cap. We have around 700 square degrees and a redshift distribution that goes from 0.6 to 1.1. This gives us approximately a 1 gigaparsec cubed volume, and we have 200,000 emission galaxies, which give us a number density of 2 times 10 to the minus 4 approximately. Then the other ingredients is the simulated dark matter halos. Why we want to relate galaxies to dark matter at all? Well, first, because galaxies live in dark matter halos, they form in the dark matter halos, and dark matter halos are better understood from the theoretical point of view. You can have models from first principles about halos, from spherical top half collage, Bretschetter, big program split model, halo model, etc. All of these are based on the halos, which are basically collapsed regions of dark matter. And we can have large simulations in which typically for the very large simulations, you can only simulate dark matter and not the baryons. And basically here we will use the halos from the outer ring simulation, one of these big simulations. And we want to study the relation between dark matter and galaxies. So the outer ring simulation that we are using is a 3 gigaparsec box, quite large, with 1 trillion particles and a mass resolution of 2 times to the 9 solar masses. It uses WMAP7 cosmology. And what we take from here is mainly the halo catalogs. We study first the clustering and the abundance of halos. So basically the halo mass function, how many halos we have per mass beam. We convert this halo clustering to just a bias function, basically what is the amplitude of the halo clustering for the different mass beams, and we get this this function that can be approximated by a 4-order polynomial. So we will use basically these 2 functions to integrate them to get some basic constraints on halo occupation distribution. And okay, so what is the halo occupation distribution model? I was saying that is one of the models to connect the galaxies to the halos. What it assumes basically is that if we know where the halos are, the clustering of galaxies will be determined by how the galaxies occupy these halos. Okay, when we analyze the 2-point correlation function, we count in pairs. We'll have contributions from pairs within the same halo, because we can have several galaxies in one halo. And this is the one halo term, and then we will have pairs coming from galaxies in separated halos, and this will be the 2 halo term that will affect mostly large scales. And how we do this sampling will determine this clustering. Following one of the original papers, we can see that there's 5 main properties that will affect the clustering. The first one is the mean halo occupation distribution. How many halos, so how many galaxies we put in each halo, and this will depend on the mass of the halo, of course. The more massive the halos, in principle, we expect more galaxies in it. This is the main thing, but then we have many other directions. So how we go from the mean occupation to the actual occupation, because there will be a probability distribution function here. We will play with this later. We will also see that we have, on the one hand, 2 types of galaxies. Some will be central, so will be located at the center of the halo with the same position and velocity as the halo. And the other ones will be satellites. And these satellites won't have exactly the same position or the same velocity. And then we need to define how we assign those positions and those velocities following a profile around the center of the halo. Okay, those are the other properties that will affect the one halo term. If we only care about large scales, then we only need to know this one. If we care about also small scales, then we need to know very well all these details. These give us a connection between the galaxy clustering that we can observe with galaxy formation and revolution. Or also, if we are more interested in cosmology, we can study this because we might think that this could be a source of systematic error for the theoretical computation of galaxy clustering. So let's vary all these details and see what happens. The canonical shape of the HOD is this one. So this is what it was defined first as the HOD. This is meant to be for if you want to study the occupation of halos by any galaxy, so all galaxies that are in the universe. So you can imagine that the central will go from 0. When the halo is not massive enough, it won't form a galaxy, but at some point, after some threshold, it will form one galaxy. So it's a step function. Whereas the satellites is more a power law. The more mass you have, the more galaxies you expect to have. And in this case, we are focusing on emission line galaxies, so we don't want to have this going to 1 necessarily. We will have some factors that will account for the incompleteness of the sample, because we only are caring about not all the galaxies, but the ones that are emission line galaxies. And typically, the emission line galaxies are galaxies that have a very high star formation rate. Okay, so it's a very specific type of galaxies. So we want to control a completeness in the centrals and a completeness in the satellites. So these 3 parameters, the 2 completenesses here and one scaling relation, let's say we can move this from left to right with this mu value, will control simultaneously the total number density. We can move things up and down. The total, the fraction of satellites, if we move the relative amplitude of these 2, the centers and the satellites, and the bias, if we move things from the left to the right, because the more massive halos have a larger clustering, a larger bias. As I was saying, not all galaxies are emission line galaxies. So what can we expect about the shape of this halo occupation distribution model? We go back to previous studies, in particular, this one by Violeta González Pérez using gulf form, and we see what shape this has. We see that it's not the step function I was showing you before. The power law is still there. So we fit this with a power law for the satellites, and we try first with a Gaussian to fit this peak here for the centrals. This Gaussian is obviously not great, so we try something else. We try this thing which is half a Gaussian until this point, and then a decaying power law. This is what we will call HOD3. And for all of them, we also use a power law for the satellites. And we see that it fits very well those data. And then we can put basic constraints on HOD. I was saying that basically these amplitudes will constrain the number density. We know the number density of our sample, the ELGs. And we also can measure the amplitude of the clustering and measure the bias of the ELGs. So we can put already some constraints on this by changing the model and integrating the halo mass function again times the bias function. And this is just the occupation distribution model that we have just defined. So how many galaxies you have per halo in average. Okay, so we can also additionally choose the number of satellites, the fraction of satellites, which is just the same integration, but with only the satellites and divided by total number. And yeah, let's vary it and see what happens. Okay, so again, I will look mostly at I look sometimes at the 2-point correlation function, sometimes at the monopole, which is the isotropic one, the quadruple that mostly looks at the line of sight to look at the velocities, and then the projective correlation function, which is unsensitive to the velocities. So the first thing, let's change the shape of the HOD and see how the clustering changes. We have so far the same fraction of satellites for 3 of them, same number density and same bias. Because we have the same bias, we have the same amplitude here. And we find on the projective correlation function small differences here in the one halo term, small scales, which are due basically to sampling different halos. So we have some variations here, but not very big. We also have some variations in the quadruple, but also very small and only at very small scales. These scales are not ones that you would look at for cosmology. Then let's say what happens if we vary more things. We now also vary the fraction of satellites. I only do this for the HOD3. The HOD3 will be the default one, so the one with the skewed shape. And then we see what is the effect of all these variations. So far, we're only varying the mean halo occupation. I didn't show this one before, but the monopole basically is not affected by any of these things, because it would be affected if we were looking at smaller scales. But for simplicity, I want to do that. I just showed this one that's saying that at cosmological scales, it doesn't vary. And then I will try to split the things between the projected correlation function that is more sensitive to small. In this case, we're looking at the small scales. And in real space, this is kind of real space. And this is very sensitive to the relative space part. So basically very sensitive to the velocities. And we see that if we vary the fraction of satellites, we have a large variation on the projected correlation function. And we also have a large variation in the quadruple. This is because satellites don't have this finger of God effects, basically have a dispersion on the kind of a random component in the velocities, because it's just the random component of satellites moving around the halo. And this basically erases the signal. It goes more to the zero part when you have all this finger of God effect, all this. If you have more satellites, you will have more of this effect. Then we study the probability distribution function for satellites. So when we have a expected number, how we go from the expected number to a realization, typically people do a Poisson, and this is what we do by default. But there are some studies in the literature that were suggesting that maybe you need to increase the scatter to reproduce the physics of galaxy formation. So we tried that as well. Basically, we have a scatter which is larger by if we have a beta of 0.1, it means at 10%. And we also try another distribution with a lower scatter. So it's just if we have a mean of 2.3, we either choose 2 or 3. For the case of centrals, we only choose 0, 1. So we will always be using this distribution. So this is kind of, we see how we go from the lower scatter, where we have a sharp distribution, to more and more scatter. We have more likely to have triplets or 4 galaxies in one single halo. And this will obviously affect the clustering, because if you have more pairs or more triplets or more occasions with 4 or 5 galaxies in one halo, this will increase the clustering of the one halo term. We have many more pairs here when we increase the scattering distribution. This won't affect much the quadruple, because we don't change the velocity, but it affects at small scales because of the same effect. Okay. If we now have to decide where we put the galaxies, typically people do an analytic narrow frame wide profile and just put randomly following this profile. This will also be our default. But some studies in literature were suggesting that emission line galaxies are galaxies that are typically outside of the halos, because once an emission line galaxy has a strong formation rate, falls into the center of the galaxy, typically the star formation rate stops because of that passing through the center. So we only see them at this before they fall into the center. So because of that, we introduced this rescaling of the concentration. Basically, we want to deconcentrate the distribution of satellites, and we introduce this factor K. Other alternative is to use just dark matter particles from the halo. And the other option is to use those particles, but also deconcentrate them. So basically move them to the outskirts by a factor of K again. So when we try this, we get a lot of different profiles. So this is how the satellites are, what are the distance to the center. And when we vary K, this varies a lot. and the particles also don't look like the NFW actually, in this case. But when you look at the correlation function, the changes are mild. They're not as big as maybe you would have expected by these big changes that you find here. But the changes are there, and these are all due to the profiles. We don't see any change on the quadrupole because we don't change the velocities. Now let's change the velocities. So by default, we use the viral theorem. So basically, you have the satellite galaxies have a velocity which are centered around the halo velocity, but with a dispersion. This dispersion is given by the viral theorem. But there is also some discussion in the literature about the velocity bias and that this dispersion could be larger for satellites. So we put this alpha factor here. That is the velocity bias. We can also use particles, and if we use the particles for the radial profile, we also use the particle velocities. We can also rescale those velocities with the same factor, the alpha factor. And additionally, because I was saying before that the mission line galaxies tend to be infalling to the halo, this typically gives them a positive velocity, an infall velocity, which is a peak here, this peak of around 500 kilometers per second, coming from this fact that mission line galaxies tends to be always infalling to the center. So we will also model this. And we get all these distributions. So with different velocity bias, we get different dispersions around the center, which in this case is 0. We got also the particle profile, which is a bit different. And we also have the infall profiles. Basically, everything's moved to the -100. What we see is that the predicted correlation function is quite insensitive to this. The only difference is whether we use narrow frame white or particles. So this is about the radial distribution, not about the velocities. But the velocity changes dramatically the 2-point correlation function on the quadrupole, even at scales around 40 or even 50 megaparsecs. Okay, so what happens if we constrain models with this? We try to constrain all these models with the data. The first, so the data we take is the mission line galaxies for EVOs. We take the monopole, the quadrupole, and the projected correlation function up to 0.02 megaparsec. So the first thing we want to constrain is this concentration rescaling I was saying. So basically, we get a best fit of around 0.25. So basically, mission line galaxies are a factor of 4 less concentrated than typical NFW profiles or typical dark matter profiles, let's say. And we get a large fraction of satellites, around 50%. And most of the constraints is coming from the projected correlation function. We don't get much constraints from the value from the quadrupole. The next thing we try, so these are a lot of evidence in favor of under-concentrated ELG profiles. The last thing we try is the beta parameter, the scatter on the PDF. We get some evidence for sub-Poissonian, but we will see that this will change as soon as we change anything else in the model. And the other interesting part is when we look at this velocity bias, basically, and we get velocity bias of 1.5, mostly coming from coming from a combination of the WP, the projected, and the quadrupole. We get this best fit, and this gives us basically that the dispersion of velocities is around 50% larger than it would have been in the viral theorem predictions. But if we also include this infall velocity that we were talking about, this 500 kilometers per second velocity infall, if we add it, then we see how the full constraints shift to the left and we recover the 1. So basically no velocity bias in this case. This is the comparison between the two. We see that this -500 just moves everything to the left. I was mentioning the use of profiles. We see there's not much changes. Okay, I'll go a bit quickly through this because I think I'm running out of time and I still have other things to talk about. But basically the beta thing, the superposition and PDF evidence goes away, but the evidence for under-concentrated profiles still remains. Okay, the factor changes a bit, but it still remains that the ELGs are under-concentrated. Then we have still the same evidence for velocity bias, kind of the same fit. These fits are a bit noisier because it's a bit more difficult to have large numbers here. But then let's wait, go back a second and say, okay, but you're varying basically how you put the profiles, how you put the satellites in the halo. What happens if you actually change the shape of the mean HOD? Because that's what everybody does in the literature, right? People just change the shape of it. So if we go back to this plot where we choose the 3 different HODs, and we rerun all the analysis, what we find is that everything stays mostly the same. The only thing that changes is the fraction of satellites we get when we go from the original one to the HOD one, which is this one. So this is the default, and this is the HOD one. The only thing we see is that the fraction of satellites reduces for all of them, but the beta, the K, and the alpha remain the same. And if we go to the other extreme case, sorry, HOD one is this one, and the other extreme case is HOD 2, which is this one, then the direction, the shift is to the other side. The fraction of satellites gets much higher than in the original case, but again, we still have the same PDF, the same concentration, and the same velocity bias. So that basically what we say is that the shape is subdominant. And then we study the generacies between all of this, but I think I'll just skip this. And if you want, you can look it up in the paper. But basically the conclusions remain the same. So what are the conclusions of all these fits? There is a clear and consistent preferences for under-concentrated profiles. So instead of 1, we have between 15 and 4, depending on the model. So basically less concentrated profiles for the mission line galaxies. We need this factor if we want to get a good fit in the clustering. The mean halo occupation distribution shape is subdominant. It's only reabsorbed by a different fraction of satellites. We have some evidence for velocity bias, but it goes away in some cases, like if we include the infall velocity, basically. So we have evidence for either the two, velocity bias or infall velocity. We have some slight preferences in the chi-square for the particle profiles with respect to Naroff and White. And the fraction of satellite varies a lot on the rest of the assumptions of the model. So it goes from 22% to 70%, although most of them are around 50%. And something similar happens with the PDF that changes a lot when you change the model. So it can be sub-Poissonian, Poissonian, or super-Poissonian. But the other ones remain more clear, that we have under-concentrated profiles. Okay, so the last part is to talk about cosmology. So I was putting this all the time in the context of we want to study cosmology. So is this relevant? All this one halo terms, so basically things that happen within the halo, can that affect the way we constrain cosmology? Well, we run the pipeline we use for EVOS in all our mocks, in which we vary the mean halo occupation distribution, the PDF, the position profiles, and the velocity profiles. And this is all based on the same halos. So we are only changing the way we populate those halos. And we measure rest speed distortion, radial VAO, angular VAO, the same way it was done for EVOS. And we find some scatter at a maximum of around 2%. So we can get deviations of around 2% depending on the model. So this is something that a priori can be worrisome. And we need to carefully look for it in the details. For EVOS, we showed it was not important. The gray bands represent the errors we reported as on our theory because of this test, basically. For EVOS, basically this is the 2%. And it was fine for EVOS because the statistical uncertainty, especially for the mission line galaxies sample, was large compared to this 2%, so it was fine. But we need to be very careful for next generation. That's why I'm talking about stage 4 experiments. DESI and Euclid are coming up and they want to measure sub-percent cosmology. So we have to be very careful with all of this. And one, again, you may still be wondering, by how can it be if it's the one halo term affecting the cosmological effect? So first, remember that the velocities can affect things all the way up to 40 or even 50 or even 60 megaparsecs, more, let's say 40. But these scales are used for cosmology already in the quadrupole. Also, the plots I was showing before about the constraints were based on power spectrum. So let's look at the power spectrum, because in Fourier space, things are more mixed up. In real space, sorry, in configuration space, things are more separable. But here things become mixed up. So even in the fraction of satellites, you see large variation of K of 0.2, 0.3. And bear in mind that right now, surveys are using these scales. Typically, surveys are fitting cosmology up to K of 0.3. So we see large variations here. So we have to be very careful at being able to marginalize the effects of satellites, thinking of God effects, etc. So fraction of satellites is important. PDF, not so much, but still, it affects, okay? The position profiles, it's less relevant because this affects really the small scales. But the velocity profiles, again, are very important. Okay, the velocity profiles can affect scales even at 0.15, which is considered nearly linear, but in some literature. Okay, so we have to be very careful here and make sure that our model is able to recover all of this. So yeah, I will link that with the Outlook. So what's coming next? We have DESI, Euclid, SKA. So DESI is already taking data. We are just started the 1% survey, I think this week. So it has 5 robotic fibers. It's a very similar setup to SDSS, so fibers to measure spectra of galaxies. And we get 30 million redshift in 5 years. So bear in mind that the amazing results I presented at the beginning from SDSS over 20 years, they covered around 2 million galaxies. And now here we will have 30 million galaxies. So imagine what we will be able to do. And data is already here, and we are preparing with a student, Violeta and Bernard, we are preparing some mocks for DESI. So we want to run similar test, HOD mock challenge again there to test the theory is good enough to all these variations of halo galaxy connection. So we are already preparing mocks for them. We also have Euclid coming up. Launch will be within 2 years, and Euclid can be regarded as 2 experiments in one. It will have basically will study the entire extragalactic area and redshift 0.9 to 1.8 with 30 million galaxies with a spectroscopic survey, and it will also have a photometric survey for Ensign. So we are also planning to run some HOD mock challenge specifically for Euclid, because again, we need to make sure that the theory we will be using it's good enough and can cope with different models of galaxy formation. So in that direction, we're moving forward with new simulations in a local group. We are running the unit simulation. Well, we have the unit simulation, and the dark matter was released a long time ago, but now we also just released a paper with SAGE, the analytical model of galaxy formation. So basically galaxies here with emission lines, and particularly with H-alpha emission line galaxies, which are the ones observed by Euclid. So you can also look for the data in this paper, because we also have the data is publicly available. And we are also studying with another student the halo occupation distribution model for this type of galaxies, and study all the details that go into the connection between halos and galaxies. So yeah, we need to prepare, but I just want to mention one last thing, a bit for fun, because we always talk about Euclid and DESI, but there's also other experiments, and I think it's very exciting to form also part of a square kilometer array, which even if it won't finish construction until probably like 2030 or something like that, But I think it's very exciting because it will study the largest scales in the universe. Let's go to Redshift. We will have an intensity mapping program up to Redshift 3. And with, again, a student, Bernard, who is actually, I think, online, we are studying how we can measure BAO with SKA and what is also the influence on the connection between dark matter and, in this case, H1, which is the observable for SKA. And I will finish here, maybe just briefly saying that, yeah, we have dissected the HOD model for the case of emission line galaxies. We have seen how all these details vary, the galaxy clustering, and motivated by previous studies. We have seen that the satellite assignment is very, very important, even more than the mean halo occupation distribution shape. So we need to know very well what happens with the PDF. We need to know what happens with the profiles, the way we put positions and velocities for the satellites. And we find actually strong evidence, even from data, that the ELGs are under-concentrated. And this is a key piece to fit the data, the clustering of ELGs. This galaxy halo connection needs to be understood very well if we want to do sub-percent cosmology, because it affects cosmological scales in the power spectrum. And yeah, so we need to be very careful with future surveys. And particularly, this is very relevant for Euclid and DESI, that will rely mostly on emission line galaxies to put constraint on cosmology. So yeah, thank you for your attention, and I will take questions.
Thank you, Santiago, for the remarkably interesting talk. We now have time for questions from the audience. If you joined us on YouTube, you can put your question in the comments and I will redirect it to Santiago.
So hi, Santi. Hi, Santi. I have a couple of questions for you. So thanks for the talk. So the first question is, do you think that the halo model is accurate to sub-percent level? There's usually a problem with in the power spectrum. So there's usually a problem with the transition from one halo to two halo terms. Can you expand on that?
Yes. Well, I don't think I have a plot for that, but so the key thing here is I'm not using the halo model to feed the data. So originally the halo model and the halo occupation distribution model was coming from the same side, but I think now what I'm referring to here is not so much about, I'm not using the halo model to constrain cosmology. I'm using the halo occupation distribution model to populate halos with galaxies, and then the model that is used to analyze the data is not that one, okay? So this model is based on TNS, resistive distortion and perturbation theory. And I think that's the lines to analyze the data is in those directions, not using the halo model to constrain data.
Okay, and one further question is that people are using now this effective field theory for galaxy bias. And do you think this is a good alternative to the HOD description?
I think, I mean, I'm not an expert on the theory side on all of this, but I think what I've heard, it seems to work well. But I wouldn't consider it as an alternative to the HOD itself, because we use HOD to populate galaxies. And what I'm trying to say here is, my approach here is, we don't know exactly what is the connection, but we know some hints of how is this connection. So let's try to simulate all those possibilities and make sure that any model we use, whether it's EFT, whether it's TNS with perturbation theory, or even if the halo model works, all of them should be tested against all the simulations. That's kind of the point. But yeah, if they work against the simulations, I would say let's use it. But I think probably perturbation theory will work. Probably EFT will work. Probably not halo model only.
Okay. Thank you, Santi.
Thanks, Rogério. More questions? Okay. We still have time for more questions.
Hey, Santi.
Hi, Juan.
Just a small question. I think you probably mentioned about that, but about this figure that you're showing there. In principle, this figure, I mean, the body of your work was with the correlation functions, if I understood well. And I presume this is, I mean, these fits are for the correlation functions only?
No,
maybe.
No, this is for the power spectrum. Yeah, this was, so I mean, in this paper, we were looking at different things. So we were not looking at, so I was studying how it affects the correlation function because it's more visual, I would say. You can see the projected correlation function, it's affected by the radial profile, for example, and the quadrupole is more affected by the finger of God effect, basically. And it's more visual, so I was studying that one. But in the app, well, let's say in the appendix, if you go to the paper, it's in the appendix, or here I also presented at the end. Also, how it affects the power spectrum, and it's also very interesting because there's not a one-to-one correspondence.
Yeah.
So, for example, the position profiles here are completely negligible in this case, whereas it was not so negligible in configuration space, or I don't know. I think it was very interesting when because I did all the study first in configuration space, and then I went to Fourier space, and things were a bit surprising when I went to Fourier space. So there's not such a one-to-one correspondence. But anyway, coming back to the question, basically this is done with the power spectrum. There is another paper, Alan et al., in which this is called the HOD challenge, in which we use only a subset of these MOCs. And in that subset, we have fits from both the correlation function and power spectrum.
Yeah,
because of time, actually, for this one, we only could have the power spectrum. That's, yeah.
Actually, that was the question. Sorry, because I was confused. Yeah, I just wanted to make sure that I was understanding that this was done with the power spectrum and not with the correlation function. And I was about to ask you about that, about the consistency between both things, because this pretty interesting differences on the effect of the different pieces of the HOD and the different changes on the HOD. If you have a sense of if both things are giving the same kind of results, at least for the scales that EVOS is presenting. That's more or less what people did, I presume. But people have a sense on some places where there can be differences on the, for example, on the Alcock-Paczynski record parameters or something like that. And if, for example, some of these effects, like, I don't know, one of those is more important for the power spectrum. So probably you have to take more care about the power spectrum for recovering the cosmology when you use the power spectrum, or everything, or in principle you can go safe doing power spectrum or correlation function as is done in the EVOS analysis.
So I think if I get correctly your question, so a priori I would be more worried about the power spectrum because the correlation function is more separable. I was showing the only worrisome thing would be the quadrupole maybe, or the hexadecapole, but sorry, what is the? I mean, here most of the cosmological constraints don't come from very. I mean, if you try to use this one, yeah, you will get lost. But the current EVOS analysis was starting at 30 megaparsec. You already have some effect, but here is a mild effect. In your model, you will always include things like the finger of God, bias, and even nonlinear bias. And they should be taking care of those, at least at first order. And that's why I think if you are here, you should be fine. If you try to fit here, I think you won't. But in configuration space, things are more separable. Let me go to the examples. So even if we were looking sometime, even if we were saying, for example, here is a large effect. It's a large effect, but it's all below 1 megaparsec. This is because we are looking at the periodic correlation function because we want to look at it. But these scales, a priori, you won't use them for cosmology. This is interesting for the HOD model, but for cosmology in configuration space, it's not relevant. You can easily cut, well, we say we cut at 30 megaparsec. So 30 megaparsec is this one, right? So we're using cosmology from here. So what happens here, it doesn't matter. For the quadruple, it's not so much the case. For the quadruple, it's a bit more affected, and we can worry a bit more. But as long as to first or second order you correct for finger of God effect, it should be fine. But on the power spectrum, things are much more mixed up, and even things that are considered simple. Sorry, I will just. So even so right now we are cutting up to K of 0.3, and the variations that you see here are huge. Okay, 20%. This is 100% variation on the quadruple. So variations here are huge. We are using this for cosmology right now. Euclid wants to go even further than 0.3. We'll see if we will use it or not, because we have to test it. But the original people from idea in Euclid was using up to K of 1. I don't think we will reach 1, but maybe 0.5, who knows? But you need to have a very, so here it's more complicated. So that's why if we have to worry about one of the two, let's worry first about the power spectrum.
Okay, thanks.
Thank you, Hugo. We might have a little time for a last question. Okay, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And
Thank
for the
you very
next, okay, thanks, Santiago. For the next week, instead of our regular webinar, we will be celebrating LIneA's 10th anniversary with a workshop focusing on the future of data centers and e-science institutes. You can find more information on LIneA's website, and registrations are still open till tomorrow. So thank you everyone and for attending, and a special thanks again for Santiago. Thank you, Santiago, for giving us a little bit of your time and for this very interesting talk. So everyone,
organizing. Thanks.
Thank you, Santi. Thank you. Bye-bye.
Bye.
Bye-bye, everyone. Have a great day. Stay safe and hope to see you all next week.
Fica aí, Rodrigo. Rodrigo.